Good evening, and welcome back to The Resting Researcher. Tonight, we're exploring one of nature's most patient art forms, something that forms in darkness, deep within the earth, over thousands or even millions of years. Something that follows rules so precise, they seem almost impossible. We're talking about crystals, not the mystical kind you might find in gift shops, but the real geological wonders, the actual atomic architecture that creates some of the most beautiful structures in nature. Before we begin, I'd love to know where you're listening from tonight. And if you're finding these gentle explorations helpful for unwinding, please consider subscribing and liking this video. It helps more people discover this quiet corner of science. I hope this journey into the mineral world is just interesting enough to hold your attention, but calm enough to let you drift peacefully into sleep. And if you do stay awake through it all, at least you'll know a little more about the geometric poetry hidden in stone. So settle in, get comfortable, and let's descend into the slow, patient world where atoms arrange themselves into perfect patterns, one layer at a time. Pick up any rock, any pebble from the ground, and you're holding billions of atoms arranged in patterns. Most of the time, those patterns are jumbled, chaotic, locked together in no particular order. But sometimes, under the right conditions, those atoms do something remarkable. They organize themselves. They line up. They repeat. That's what makes a crystal. Not magic or energy fields, but simple geometry. Atoms stacking in three-dimensional patterns that repeat over and over, creating structures so regular you could predict the position of every atom inside. Think of it like this. Imagine you have a room full of spheres, identical balls that can stack together. If you drop them randomly, they'll pile up in a messy heap. But if you carefully place them one at a time, following a pattern, sphere touching sphere, in the same way every time, you'll build something organized, something structured. That's crystallization. Atoms acting like those spheres, finding positions where they fit together most efficiently, then repeating that arrangement billions upon billions of times. The pattern they follow is called a crystal lattice. It's the invisible scaffolding that determines a crystal's shape. And remarkably, there are only so many ways atoms can arrange themselves in 3 dimensions while maintaining perfect repetition. Scientists have identified exactly 7 crystal systems, 7 fundamental patterns that govern how every crystal in the universe forms. It doesn't matter if you're looking at a grain of salt or a massive quartz formation. The atoms inside follow one of these 7 basic blueprints. Let's meet them slowly and gently. The first is the cubic system. Imagine a perfect cube, equal sides, right angles everywhere. Salt crystals follow this pattern. So do diamonds. Each sodium and chloride atom in table salt sits at the corner of an invisible cube, and that cube repeats in all directions, forming the larger crystal you can see with your eyes. When you look at a grain of salt under a magnifying glass, you'll often see it's actually a tiny cube. That's not coincidence. That's the atomic lattice, expressing itself at a scale you can see. The macro shape reflects the microstructure. Then there's the tetragonal system, similar to cubic, but stretched along one axis. Imagine taking that cube and pulling it taller. The base remains square, but the height changes. Certain gemstones like zircon follow this pattern. The orthorhombic system is another variation. 3 unequal axes, all at right angles. Picture a shoebox, different length, width, and height, but everything still perpendicular. Sulfur crystals often form this way, creating elongated rectangular shapes. The hexagonal system is perhaps the most elegant. 6-fold symmetry. Think of a honeycomb. Quartz, one of Earth's most common minerals, crystallizes in hexagonal prisms. If you've ever seen a clear quartz point, That six-sided column shape isn't random. It's hexagonal symmetry made visible. Snowflakes also follow hexagonal patterns, though they're made of ice, not rock. The six-pointed arms, the intricate branches, all stem from the hexagonal arrangement of water molecules as they freeze. The trigonal system is related to hexagonal, but with threefold symmetry instead of six. Calcite follows this pattern. It's the mineral that makes up limestone and marble, and it has a peculiar property we'll explore later. Then there's the monoclinic system. Here, two axes are perpendicular, but the third tilts at an angle. Imagine a box that's been pushed slightly to one side. Gypsum, the mineral used to make plaster, crystallizes this way. Finally, the triclinic system is the least symmetrical. All three axes have different lengths and tilt at different angles. It's like a box that's been pushed and pulled in multiple directions. Yet even this apparently chaotic arrangement repeats perfectly, creating a genuine crystal structure. These seven systems might sound abstract, but they explain something profound. They explain why crystals have the shapes they do, why quartz forms hexagonal prisms, why salt makes cubes, why diamonds have eight-sided faces. The external shape is a consequence of the internal order, geometry expressing itself in stone. But crystals aren't just about shape. They're about growth, about how something invisible becomes visible, how individual atoms, drifting through liquid or gas, find each other and lock into place, building layer by atomic layer. Crystal growth is one of nature's most patient processes. It requires time, stability, and just the right conditions. Too much heat, and atoms move too quickly to settle into position. Too much cold, and they lock randomly before finding their proper place. The sweet spot, the temperature and pressure where crystals thrive, is often narrow and specific. In many cases, crystals form from solutions. Imagine salt water slowly evaporating. As water molecules drift away into the air, the dissolved salt becomes more concentrated. Eventually, there's not enough water to keep all the sodium and chloride ions separated. They begin to meet, to bond, and the first tiny crystal seed forms. Once that seed exists, other ions find it easier to attach to its surface than to start new crystals. The existing lattice acts as a template, guiding new atoms into position. The crystal grows, layer by layer, following the pattern set by that first seed. This process can be astonishingly slow. Deep underground, in cavities within rock, mineral-rich water seeps through cracks. A single drop might carry only a few dissolved atoms. As that water evaporates or cools, those atoms settle onto a growing crystal. Then, another drop arrives, and another. Over centuries, a quartz crystal the size of your thumb might form. Over millennia, one's the size of your arm. In some caves, conditions have remained stable for so long that crystals have grown to truly massive sizes. The Cave of Crystals in Nica, Mexico, contains selenite beams longer than school buses, some weighing over 50 tons. They grew in a water-filled cavity, heated by magma below, where temperatures stayed near 58 degrees Celsius for 500,000 years. 500,000 years of patient, uninterrupted growth, atom by atom, layer by layer. But not all crystals form from water. Some crystallize directly from molten rock. As magma cools deep underground, minerals begin to solidify at different temperatures. The first to crystallize are often the densest, heaviest minerals. They sink, leaving the remaining magma enriched in lighter elements. This process, called fractional crystallization, is how granite forms. Different minerals, quartz, feldspar, mica, crystallize at different times, creating the speckled pattern you see in countertops and headstones. Even volcanic glass, like obsidian, is a kind of failed crystal. It's rock that cooled so quickly, the atoms didn't have time to organize. The result is an amorphous solid, glass instead of crystal, smooth and structureless. As we settle deeper into this exploration, picture what's happening at the atomic scale. Invisible forces guiding particles into position. Chemical bonds forming one after another in perfect repetition. A structure emerging from chaos, not through intention or design, but through the simple physics of attraction and geometry. It's architecture without an architect, order without instruction, and it's been happening beneath our feet, in darkness and silence, for billions of years. Crystals aren't just beautiful, they're functional. The geometric arrangement of atoms doesn't just determine shape, it determines behavior. How light moves through them, how they break, even how they respond to pressure or electricity. Let's start with something you can see. Transparency. Many crystals are transparent or translucent, allowing light to pass through with minimal scattering. This happens because their atomic structure is so regular, so perfectly ordered, that light waves can travel through without encountering irregular bumps or voids that would scatter them. Quartz is a perfect example. Pure quartz, made of silicon and oxygen atoms, arranged in a hexagonal lattice, is completely clear. Light enters one side and emerges from the other, barely bent or altered. It's optical-grade material, used in lenses, prisms, and fiber optics. But transparency isn't universal. Some crystals are opaque because they contain atoms that absorb light. Others are translucent, allowing some light through, but scattering it along the way, creating a milky or cloudy appearance. Then there's color. Pure crystals are often colorless, but introduce even tiny amounts of impurities, trace elements that don't quite fit the lattice, and color appears. Amethyst, for instance, is just quartz with trace amounts of iron. The iron atoms replace a few silicon atoms in the lattice, and their presence changes how the crystal absorbs light. Certain wavelengths get absorbed, others pass through, and the result is that beautiful purple hue. Rubies and sapphires are both made of aluminum oxide, a mineral called corundum. Pure corundum is colorless, but add a bit of chromium, and you get the red of ruby. Add iron and titanium, and you get the blue of sapphire. Same crystal structure, different impurities, completely different colors. This is why gemstones are so varied. It's not that nature creates fundamentally different minerals. It's that the same mineral, with slightly different chemistry, expresses itself in different ways. Now, let's talk about how crystals break. This property, called cleavage, is directly linked to atomic structure. Crystals don't fracture randomly. They split along specific planes, where atomic bonds are weakest. Mica is the classic example. It has a layered structure, with strong bonds within each layer, but weak bonds between them. As a result, mica cleaves into thin, flexible sheets. You can peel it like paper, layer after layer, each one smooth and flat. Calcite cleaves along 3 planes, creating rhombohedral shapes, geometric chunks that look like squashed cubes. No matter how you break calcite, it tends to form these same angled fragments. That's the lattice asserting itself even in destruction. Quartz, on the other hand, doesn't have strong cleavage planes. It fractures irregularly, creating curved, shell-like surfaces called conchoidal fracture. This made it useful for ancient humans' crafting tools. A sharp strike could produce predictable, sharp-edged flakes, perfect for cutting. Some crystals have another curious property. They change shape under stress. Apply pressure to quartz in the right direction, and it generates a tiny electrical voltage. This is called piezoelectricity, and it's why quartz is used in watches and electronics. Inside a quartz watch, A tiny crystal vibrates at a precise frequency when voltage is applied. That vibration is so regular, so predictable, it can be used to measure time with extraordinary accuracy, all because of the geometric arrangement of silicon and oxygen atoms. The reverse also works. Bend or squeeze quartz, and it produces electricity. This is how some lighters work. A spring-loaded hammer strikes a piezoelectric crystal, generating a spark that ignites the gas. Other crystals respond to heat. Tourmaline becomes electrically charged when heated or cooled, a property called pyroelectricity. For centuries, Dutch traders carrying tourmaline from Sri Lanka noticed that the stones would attract ash from their pipes when warmed near a fire. They called them ash pullers, long before anyone understood the physics behind it. Then, there's the optical property called double refraction. Calcite is famous for this. Place a clear calcite crystal over a piece of text, and you'll see the words doubled. Light entering the crystal splits into two rays, each traveling at a different speed, each bending at a different angle. The result is two overlapping images. This happens because calcite's atomic structure treats light differently depending on its direction. In one direction, light moves faster, in another, slower. It's not magic, it's anisotropy, the property of behaving differently along different axes. Crystals can even glow. Some minerals fluoresce under ultraviolet light, absorbing invisible UV photons and re-emitting them as visible light. Fluorite does this beautifully, glowing blue or green when exposed to a UV lamp. Others phosphoresce, continuing to glow even after the UV light is turned off. The atoms absorb energy, hold it briefly, then release it slowly over seconds or minutes. It's a delayed reaction, a kind of mineral memory. All of these properties, transparency, color, cleavage, piezoelectricity, double refraction, fluorescence, stem from the same source, the orderly, repeating arrangement of atoms in three-dimensional space. Change the pattern, and you change the properties. It's why diamonds are hard, but graphite is soft, even though both are made purely of carbon. The atoms are arranged differently. In diamond, each carbon bonds to four neighbors in a rigid tetrahedral lattice. In graphite, carbon atoms form flat sheets with weak bonds between them, allowing the sheets to slide past each other. Same element, different geometry, completely different behavior. As we pause here, think about the crystals you encounter every day without noticing. The silicon in computer chips, the quartz in your phone's screen, the salt in your kitchen, the gypsum in your walls. All of them, at the atomic level, are perfectly ordered structures, repeating patterns that have been forming on Earth for billions of years. And now, let's turn our attention to some of the most spectacular crystals nature has ever grown, and the places they hide. Crystals form anywhere atoms have time and space to organize, but some locations on Earth have produced specimens so large, so perfect, or so rare that they've become legendary in the world of mineralogy. We've already mentioned the Cave of Crystals in Nica, Mexico, but it's worth dwelling on just how extraordinary this place is. The cave sits nearly 300 meters underground, within a limestone mountain. For hundreds of thousands of years, it was filled with hot, mineral-rich water, heated by a magma chamber below. The water was saturated with calcium sulfate, the chemical that forms gypsum. And for 500,000 years, conditions remained absolutely stable. Temperature, pressure, chemical composition, all constant. In that perfect stillness, gypsum crystals grew to monstrous sizes. The largest crystal ever measured there was over 11 meters long and weighed approximately 55 tons. A single crystal, not a cluster, not an aggregate, but one continuous lattice of atoms extending across a space larger than most rooms. Walking into that cave, before it was flooded again for safety, was like entering a cathedral made of light. The selenite crystals are translucent, glowing faintly amber in lamplight. They crisscross the chamber at angles, some resting on the floor, others spanning wall to wall, like frozen beams of crystallized time. Humans can only survive there for minutes, without cooling suits. The heat and humidity are lethal, but the crystals endured it for millennia, growing patiently in the dark. Another remarkable location is the pulpy geode in Spain. Unlike the Nika crystals, which formed in an open cavity, the pulpy crystals grew inside a hollow sphere of rock. The geode is about 8 meters long, and its interior is lined with enormous gypsum crystals, some over 2 meters tall. Geodes form when gas bubbles are trapped in cooling lava, or when cavities form in sedimentary rock. Over time, mineral-rich water seeps in and evaporates, leaving behind layers of crystals that grow inward toward the center. Opening a geode is like cracking open an egg to find a palace inside. Then there's the amethyst of Brazil and Uruguay. In the volcanic rocks of southern Brazil, huge geodes of amethyst have been found, some tall enough to stand in. The purple crystals line the walls in dense clusters, each one a hexagonal prism, tipped with a pointed termination. These geodes likely formed millions of years ago, when gas bubbles in cooling lava created hollow pockets. Later, silica-rich fluids seeped in, carrying trace amounts of iron. As the fluids cooled, quartz crystallized, and the iron impurities gave it that distinctive purple color. Now let's travel to Arkansas, known as the quartz crystal capital of the United States. The Ouachita Mountains contain vast pockets of rock crystal, clear quartz formations that have been prized for centuries. Native Americans used them for tools and trade. Modern collectors seek them for their clarity and size. Quartz is one of the top, most common minerals on Earth, making up a significant portion of the continental crust. Yet perfect gem-quality specimens are rare. Most quartz is microcrystalline, tiny grains fused together. Large, clear crystals require open space, stable conditions, and time. In Madagascar, rose quartz forms in massive deposits. The pink color likely comes from trace amounts of titanium, iron, or manganese, though the exact cause is still debated. Rose quartz rarely forms well-defined crystals. Instead, it occurs in massive chunks, translucent and softly colored, often used for carvings and ornaments. Then there's Iceland spar, a transparent variety of calcite found in Iceland. It's so clear and exhibits such strong double refraction that it was historically used in navigation. Vikings may have used it as a sunstone, a tool to locate the sun's position, even through clouds, by observing how polarized light split when passing through the crystal. In the deserts of Arizona and Mexico, you'll find chrysocolla and malachite, bright blue and green copper minerals that form when copper deposits oxidize and interact with groundwater. These aren't gemstones in the traditional sense, but their vivid colors make them highly prized for jewelry and decoration. Deep in the Ural Mountains of Russia, alexandrite was discovered in the 1830s. It's a variety of chrysoberyl that appears green in daylight but red under incandescent light. This dramatic color change happens because of how chromium impurities absorb different wavelengths depending on the light source. It's one of the rarest and most valuable gemstones. In Sri Lanka, gem gravels contain sapphires, rubies, garnets, and zircons, all eroded from ancient metamorphic rocks and concentrated in riverbeds. For centuries, miners have sifted through these gravels, finding crystals that formed deep underground and were later brought to the surface by geological forces. Australia is famous for opals, but opals aren't technically crystals. They're amorphous, lacking the repeating atomic lattice that defines crystalline structure. Instead, they're made of tiny spheres of silica, packed together, and the spacing between those spheres creates their play of color through light diffraction. Still, opals remind us that not all beautiful minerals are crystalline. Sometimes disorder can be just as stunning as order. Now let's consider the crystals that form in our own bodies. Bones contain hydroxyapatite, a calcium phosphate mineral that crystallizes in a hexagonal system. It's what makes bones hard and strong, a natural ceramic scaffolding grown cell by cell. Unfortunately, crystals can also form where we don't want them. Kidney stones are often made of calcium oxalate crystals. Gallstones can be crystalline cholesterol. Gout is caused by uric acid crystals forming in joints. In these cases, the same atomic forces that create beauty in caves create pain in bodies. Even teeth contain crystals. Enamel is packed with hydroxyapatite, making it the hardest substance in the human body. Every time you chew, you're relying on the geometric strength of a crystalline lattice. Crystals are everywhere, in the ground beneath you, in the technology around you, even inside you. They're the Earth's way of organizing matter, of turning chaos into structure, one atom at a time. And in the stillness of caves deep underground, they continue to grow, invisible in the dark, patient beyond measure, waiting, perhaps, for the day someone discovers them and brings them into the light. For most of human history, crystals were valued for beauty or rarity, but in the modern world, they've become indispensable, not for mysticism or decoration, but for function. The unique properties of crystalline structures underpin much of our technology. Let's start with something you likely have in your pocket: a smartphone. Inside it are dozens of different crystals, each serving a specific purpose. The screen is made of glass, which is technically amorphous, but it's strengthened with crystalline coatings and sits above a layer of liquid crystals. These liquid crystals can change orientation when voltage is applied, controlling how much light passes through each pixel. It's how your screen displays images. The processor, the brain of the phone, is built on a silicon crystal wafer. Silicon is grown into a pure single crystal, sometimes a meter long, then sliced into thin wafers. These wafers are etched with billions of transistors, creating the integrated circuits that make computation possible. Quartz oscillators inside the phone keep time. A tiny quartz crystal vibrates at a precise frequency, exactly 32,168 times per second, providing the heartbeat for the device's clock. This is the same technology used in wristwatches since the 1970s. Even the speaker relies on crystals. Piezoelectric materials convert electrical signals into vibrations, which become sound waves, its crystalline structure transforming energy from one form to another. Beyond phones, crystals are essential in optics. Lenses, prisms, and fiber optic cables often use quartz or synthetic sapphire because of their clarity and durability. The Hubble Space Telescope's mirrors are coated with aluminum, but the optical elements guiding light through the instruments rely on crystalline materials. In medicine, ultrasound machines use piezoelectric crystals to generate and detect sound waves. A crystal vibrates, sending ultrasound into the body. When echoes return, the same crystal detects them, converting mechanical vibrations back into electrical signals that form an image. Lasers often use crystalline materials as their active medium. Ruby lasers use synthetic ruby, a crystalline form of aluminum oxide, doped with chromium. The atoms in the crystal absorb energy, then release it as coherent light. Even solar panels contain crystals. Most are made from silicon, crystallized into either single large crystals, monocrystalline, or many small crystals, polycrystalline. The orderly atomic structure allows electrons to flow freely when struck by sunlight, generating electricity. In construction, we use gypsum for drywall, calcite for cement and concrete, and quartz for glass and ceramics. These aren't high-tech applications, but they're everywhere. Your walls, floors, and windows are held together by crystalline minerals. Table salt, as we've mentioned, is sodium chloride, a cubic crystal. Sugar is sucrose, which crystallizes in a monoclinic system. When you season your food or sweeten your coffee, you're sprinkling billions of tiny crystals onto your plate. Diamonds, once valued purely for beauty, are now industrial tools. Diamond-tipped drill bits cut through rock. Diamond abrasives polish metal and glass. Synthetic diamonds, grown in laboratories, are often more useful than natural ones because they can be tailored for specific purposes. And then there's graphene, a single layer of carbon atoms arranged in a hexagonal lattice. It's not a traditional crystal, it's a two-dimensional material. But it's crystalline in structure, and it's one of the strongest, most conductive materials ever discovered. Researchers believe it could revolutionize electronics, materials science, and medicine. Crystals are no longer just geological curiosities. They are the silent foundation of modern life. Every time you check your phone, turn on a light, or take a medical scan, you're relying on the geometric perfection of crystalline structures. It's a strange thought, isn't it? That something formed so slowly, so patiently deep in the earth, now moves at the speed of light through our devices. As we come to the end of our journey through the world of crystals, let's return to where we started. The idea of order emerging from chaos. Crystals are proof that nature doesn't need instructions to create beauty. Given time, stability, and the right conditions, atoms will organize themselves. They'll find the most efficient way to fit together, and they'll repeat that pattern billions of times. It's geometry without a geometer, architecture without an architect, a kind of mathematics written in matter. Deep underground, in cavities you'll never see, crystals are growing right now. Slowly, atom by atom, following patterns that have existed since the first minerals formed on a cooling Earth, billions of years ago. Some will be discovered, others will remain hidden forever, growing in silence and darkness, perfect and unseen. There's something comforting in that, isn't there? The idea that beneath the noise and chaos of daily life, there are processes unfolding at their own pace, unhurried and patient, building order, creating structure, one atomic layer at a time. Thank you for joining me on this quiet exploration of crystals. I hope it gave you a new appreciation for the stones beneath your feet, the minerals in your walls, and the geometric wonders hidden inside the earth. As you drift off to sleep tonight, picture those slow, patient processes, atoms finding their place, lattices extending, crystals growing in the dark, and rest easy, knowing that nature's most beautiful architecture happens without effort, without haste, and without ever needing to be seen. Sleep well.